Good morning, students. Today I am going to see how to find the stability for the characteristic equation using Routh-Hurwitz technique. Using Routh array, so how to form the stability for a characteristic equation. Okay. First of all, what is the stability? Stability is nothing but if we give the bounded input, if we getting the bounded output, then we can say the system is stable. In a transfer function depends upon the root location. We can say the system stability. Suppose the root lies on left half of the S-plane, mean system is said to be stable. The same root lies on any one root right half of the S-plane, mean then system is said to be unstable. Any number of roots on the left half of the S-plane, but if even one root lies on the right after the S-plane, mean then system is unstable. Okay. Similarly, suppose the root lies on imaginary axis. There is no roots on right upper the S-plane. Only the roots lies on imaginary axis as well as left upper the S-plane, mean then system is said to be a marginally stable. So these are the three main conditions. Depends upon the root location. That is, one is the left half of the S-plane, one is on the right half of the S-plane, another one is the imaginary axis. So if it is lies on left half of the S-plane, system is stable. Right half of the S-plane means system is unstable. If it is lies on the imaginary axis, system is marginally stable. Okay. So these are the depends upon the root location. We have the stability. So what is the Routh-Hurwitz technique? What is the Routh-Hurwitz criteria? So we will be forming the Routh array. Okay. So in the Routh array, so we have the different order will be there. In the Routh array, so we will be seeing the first column of the Routh array. If the first column of the Routh array is positive, then system is said to be stable. If the first column of the Routh array is, if any one negative is came, means then system is said to be unstable. So this is the main condition. So number of roots lies on the right half of the S-plane depends upon the number of sign change occurs on the first column. The number of sign change is 2, means then 2 poles lies on the right half of the S-plane. Okay. So depends upon the first column of the Routh array, system is said to be a stable or unstable. So these are the Routh-Hurwitz criteria. Okay. So now move on to the first column. So using Routh criteria, determine the stability of the system represented by the characteristic equation s power 4 plus 8s cube plus 18s square plus 16s plus 5 equal to 0. So we asked to comment on the location of the roots of the characteristic equation. So for how to form the Routh array first? So first we have to take the s power 4. For s power 4 coefficient start from here. Okay, so the coefficient is 1. So leave the next one. Next take the x square. What is the 18? So leave the next one. Next take 5. Okay. Similarly, we can write for s cube. S cube can be, what other term we have left out? 8, 16. Okay. So these first two rows can be formed from the equation, characteristic equation. Okay. So the other s power 2, s power 1, s power 0 can be, we have to form using the Routh-Hurwitz criteria. That is a Routh array we have to form. So how to form the s square? Before that, if the s cube or s power 4 is divisible, means we can divisible and write it. Suppose this s cube is divisible. 8 and 16 are divisible. So we can replace by s cube as 1 and 2. Okay. Now we can form s square. This term can be formed by previous two rows. First column. What is the first column? 1, 1. Next column 18, 2. Okay. So we have to form the root multiplication. So how to form the root multiplication? 1 into 18 minus of 2 into 1 divided by 1. Okay. We have to form, we will be getting 16. So that is the answer. Okay. So next, if you want to form this column, again first column, previous two rows first column. For this column, next column, what is the 5 and 0? 5 and 0. Again form the root multiplication. 1 into 5 minus of 0 into 1 divided by 1. So you will be getting 5. Okay. So you will be getting 5. So we'll be getting answer as 16, 5. So we got S square. We got S square. Next you have to form S power 1. So we have to form S power 1. For S power 1 first term, first you have to take previous two rows. So again previous two rows. That is S square, S power 3. Okay. So what are the term? 116, 2, 5. So 16 into 2 minus of 5 divided by 16. Okay. So I think this is the correct equation. 1 into 5. So what is this answer? 12. Okay. Minus of 5 divided by 16. Okay. So what is the answer? Check this answer. So this how much of answer is given? So in beginning 27 by 16. Check this answer. For S power 1, what is the answer you are getting? 32 minus 5 by 16. 27, 16 will be somewhat getting 1.68. Okay, just round it up to 1.7. Okay. So for this, previous two row, first column, next column 0. So already, so again we will be getting 0. So leave it up. So next S power 0, previous two rows. So these two rows, 7.5 into 5 minus 0 divided by 1.7. So again 1.7 will be cancelled, we will be getting 5. So these are the Routh arrays we have formed. Okay. In the Routh array, check the first column. First column is positive or negative. Check the first column. Here you can see the first column, what we have formed is all are positive. So the corresponding characteristic equation is stable. System is stable. Next, how many roots lies on the left of or right of the plane or imaginary axis? This you have to see. So already I have seen. If it is stable means system will be lies on the roots will be lies on the left of the plane. If it is unstable means the roots must be lies on the right of the plane, depends upon the sign change. Here the system is stable. Then all the roots are lies on the left of the plane. So how many roots are there? Totally we have the highest degree is 4. So the 4 roots must be lies on the left half of the S-plane. Left half of the S-plane. Okay. So this is the first type of problem in the Routh array type. So I think we will be clear for this axis equation. Thank you. Morning students. Move on to the next problem, that is it. Using Hurwitz, we will have the second type of problem, that is S power 6 to S power 5 plus 8 S power 4 plus 12 S cube plus 20 S square plus 16 S plus 16 equals 0. So can you solve this type of problem? Okay. So start with the S power 6. Okay. You can write the coefficient of each term leaving the next term alternatively. So what are the corresponding coefficient? 1, 8, 20, 16. Okay. So what are the term will be left out? 2, 12, 16. Just 90 for S power 5. Okay. Now you can form the S power 4 S cube using the Routh array. Okay. So you can form the Routh array. So before that, S power 5. So this is a divisible. S power 5 is a divisible. So you can use 1, 6, 8. Okay. Just divisible by 2. Now again we can form the S power 6, S power 5. Now form S power 4. So for the, if you want to find this term, what are the previous two? First column, next column. Okay. So we use a Routh multiplication. 1 into 8 minus 6 into 1 divided by 1. So we'll be getting 2. Okay. We want this term. Previous two was 1, 1, 28. So 20 into 1 minus 8 divided by 1. We will be getting 12. So we will be getting 12. Next term 8, 6. First column is 1, 1. Next column is 16, 0. So 16 minus 0 divided by 1. So we will be getting again 16. Okay. So this is also divisible by 2 we can. So s power 4 is 182. So sorry, 1, 6, 8. So you can see here both s power 5 and s power 4 are equal. If it is both are equal means you will be getting s power cube is all becomes 0. If any row with all 0, then you can't proceed the next row. That is Routh. This is one of the type of problem. Okay. So if it is come like this, so after this type of problem, the system will have a marginally stable. So this condition indicates that system is marginally stable. So how can you proceed the next step? How can you proceed the s power cube? For that, we have to form the s power 4. S power 4 is nothing but 168. So form the Cax's equation like this: s power 4 plus. So we will be having this is s power 4. Okay. So just we have to form 6x square plus 8 equal to 0. So this is take a, let it be take as a, let it be variable take a. So differentiate this a with respect to s and equal to 0. So what will happen? 4s cube 12s plus 0. Okay. So this can be written as a s cube coefficient. So 4s cube plus 12s. So s cube can be written as 4 and 12. This also you can divisible. This also if you want divisible 1 and divisible by the 4, 1 and 3. So now we can form the s square. S square form the s cube and the s power 4. Okay. So how can you form? So s power 4 is 1, 1. Next row is 6, 3. So 6 minus 3 divided by 1. We will be getting 3. We want this term 1180. 1180. So we will be getting 8 minus 0 divided by 1. So we will be getting 8. Okay. So we will be getting s power 1. If you want to find s power 1, so we will be getting just multiply this 9 minus 8 by 3. So 9 minus 8 by 3. Then we are getting 1 by 3. This 1 by 3 almost we are getting 0.33. So we are getting 0.33. And this term becomes 0. So limit of s power 4. S power 4 0.33 minus 28 minus 0 divided by 0.33 will be getting 8. Okay. So wait a minute. So now we can check the first column. So whether there is any negative term, even though it is even one row is are 0, check the first column. Is there any negative term? Is there? Already we have mentioned it's a marginally stable condition. But if we have some negative term, then it will come into the unstable condition. So check the first column. First column there is no negative term. So only we have the 0, 0 term. From that we can identify this is marginally stable. This is marginally stable. Next we have to find how many roots lies on imaginary axis, how many roots lies on left. There is no roots lies on right after the square. Since there is no negative term in the first column, there is no roots lies on right after the plane. Only the root can be lies on the left of the plane or imaginary axis. Okay. So this is marginally stable. So how can I identify how many roots lies on the imaginary axis as well as left of axis? For that, take some auxiliary equation, any one equation, even s power 4, the same equation you can take. S power 4 plus 6s square plus 8 equal to 0. Okay, put s square equal to x. Let it be s square equal to x. What will happen? X square plus 6x plus 8 equal to 0. Identify the roots first. And we will find the roots for this. So we will be getting as almost x's minus 2, minus 4. We'll be getting two roots, minus 2 and minus 4. From this, let it be x equal to minus 2. Okay? Find x square equal to x. Then what will happen? X square equal to minus 2. Then x equal to root plus or minus root of minus 2. So we'll be getting plus or minus root 2j or root 2i. So this is one of two roots, imaginary. Again, x equal to minus 4. Then x square equal to x means x square equal to minus 4. Then x equal to plus or minus root of minus 4. Then plus or minus 2j. So this is another two roots lies on the imaginary axis. So we'll have the four roots lies on the imaginary axis and two roots on the left upper exponent. So from this we can identify totally we'll having 6 roots. From this we'll having four roots lies on imaginary axis. Imaginary axis and two roots lies on left upper exponent. So this is the second type problem with the row, all the row with the zeros. Is it clear? So the row all with the 0 means the system is marginally stable, but we have to check the first column. If this any 90 means system will be considered as a unstable. Okay. Thank you. Move to the next problem, third type problem. So now this type of problem will have the zeros present on the first column. If the zeros present on the first column, how to proceed the next row. So this is a type of problem. So s power 5 plus s power 4 plus 2s3 plus 2s square plus 3s plus 5 equal to 0. So again we have to proceed with the same type. Start with the s power 5. Okay. Another coefficient 1, 2, 3. And s power 4 we are having the what are the left out we are left with 1, 2 and then 5. Okay. So now proceed the s power 3. Okay. So do the root multiplication 1 into 2 minus 2. Okay. 1 into minus 2 into 1 divided by 1. Okay. So we will be getting 2 minus 2 will be getting 0. Next, if you want this element, first column, next column 1 into 3 minus 5 into 1 divided by 1. Okay, you will be getting minus 2. If you want this column, you will be getting 0. This column, next column, that column will be getting as a 0. So 1 1 0 0. 1 1 0 0. You will be getting 0. So any row with the 0, first column with the 0 means, normally if you proceed with the next s power square means what will happen? We will be getting as some infinity. Surely we will be getting infinity if we divide by 0. Using infinity, if you want to solve the next row means it will be very difficult. We can't solve the next row that its rows. For that, we have to replace the 0. We have to replace the 0 by epsilon. We will be replaced by epsilon and proceed the row that bits. Okay. So using the epsilon, we are proceeding the row that bit s square. What is the s square? 2 into epsilon minus or minus plus 2 divided by epsilon. Okay. Again 5 epsilon minus 0 by epsilon, we are getting 5. Epsilon into 5 minus 0 divided by epsilon, we will be getting 5. Okay. Next s power 1, let's solve here, we can solve it and do it. Minus 2 into 2 epsilon plus 2 divided by epsilon minus of 5 epsilon divided by 2 epsilon plus 2 divided by epsilon. Okay. So let's solve this minus 2 and take epsilon as a LCM. So we can minus 4 plus minus 4 minus 2 epsilon. So minus 4 epsilon minus 2 minus 5 epsilon square. Okay, divided by 2 epsilon plus 2. Can you check it out? So minus 5 epsilon square minus 4 epsilon minus 2 divided by 2 epsilon plus 2. This term First column, next column 0. This term into 0 minus 0 divided by this term. So this will become 0. Okay. S power 0. This term into this term minus 0 divided by this term. This will be cancelled. We will be getting only 5. So kindly check this out. Minus 4 epsilon. Minus 4 epsilon square. Minus 4 epsilon minus 5 epsilon square minus 4. Actually minus 4 is that. Okay, so we are getting minus 4 here. This is getting minus. So let's see what. Now, if you want to proceed the stability, we have to replace the epsilon by 0 now. Now we can replace the epsilon by 0. S power 5, 1, 2, 3. S power 4 is 1, 2, 5. Okay, S power 3 is epsilon now replaced by 0, minus 2. S square is, so if you replace 0 means we will be getting infinity. Infinity 5. S power 1. So now replace the epsilon by 0. This will become 0. This 0 minus 4 by 2. We will be getting minus 2. And S power 0 we will be getting 5. Now check the first column. Now check the first column. So we have the 90 sign. The 90 sign indicates system is unstable. System is unstable. So since there is an ID term present on the Routh Hurwitz, that is the Routh array, therefore system is unstable. Then how can I identify how many roots lies on right after the S prime? So it indicates system is unstable. How many roots lies on the right after the S prime? That you have to check. So how many sign change present on the first column? So you can see here, these are all positive. Okay. So here changing from plus to minus, one sign change. Plus to minus. Again change from minus to positive, second sign change. There are two sign change. There are two sign change. Therefore, there are two roots lies on the right half of the S prime. Two roots lies on the right half of the S prime. So totally how many roots? 5 roots. Two roots lies on the right half of the S prime means system is unstable. Remaining two roots must be lies on the left half of the S prime. So this is the third condition of Routh Hurwitz technique with a single element, that is in the first column, first row. If it is 0 means proceed with the epsilon. After proceeding with the epsilon, replace epsilon by 0. Okay. So here we replace the epsilon by 0 and proceed with the Routh Hurwitz. Okay. Then check the stability, first column. So in this problem, the first column indicates there is an ID sign, so system is unstable. Okay. Number of sign change in the first column indicates the number of root size on the right half of the S prime. So generally the root necessary sufficient condition for Routh Hurwitz technique is this, that we have to check the first column should be positive. System should be stable means first column should be positive. If there is any ID term present means system is unstable. Okay. Number of roots lies on the right half of the S prime will be corresponds to number of sign change in the first column. If it is a two sign change means two roots must be lies on the right half of the S prime. I think these are the three types of problems present on the Routh Hurwitz techniques. Based on the remaining different problem will be out in the textbook. You can solve and see. Okay. Thank you. Good morning, students. Today we are going to see using Routh Hurwitz technique without giving characteristic equation. So only they are going to open transfer function. From that, how to apply the range of stability. Okay. So this is a problem. Determine the range of K for the stability of unity feedback system whose open transfer function is G of S equal to K divided by S into S plus 1 into S plus 2. So in previous problem, the characteristic equation is given in the problem itself. From that, what you have seen, what is the stability, and what you have seen, what are the location of roots you have seen. Okay. So in this problem, they given the transfer function, oblong transfer function they given with the unity feedback data. They didn't given the characteristic equation. So what is the characteristic equation? So first you have to find the characteristic equation. The characteristic equation is given by 1 plus G of S H of S equal to 0. 1 plus g of s, h of s equal to 0. G of s is the open transfer function, h of s is the unity feedback they given. So 1 plus k divided by s into s plus 1 into s plus 2 into 1 equal to 0. So s into s plus 1 into s plus 2 plus k equal to 0. Okay. So from this s square plus s into s plus 2 plus k equal to 0. S cube plus 2s square plus s square plus 2s plus k equal to 0. So we are getting s cube 3s square plus 2s plus k equal to 0. So this is the characteristic equation finding what we obtained. So using this you are going to form the Routh. So in this problem they given the open transfer function. From this we got the with unity feedback, from this we got the characteristic equation. Now the same procedure we are going to form the Routh. Okay. So what is the question? They asked to find the range of k for stability. So the system is stable. Then what is the range of k they are asking? Okay. So this is the equation s cube plus 3s square plus 2s plus k equal to 0. Okay. So let we start with the s cube. Okay. 1 corresponding question 2 for s square. What are the term left of 3 and k? Okay. So form the s power 1. For s power 1, 6 minus k divided by 3. So root multiplication 3 into 2 minus of k into 1 divided by 3. So this term will be getting 0. For s power 0, 6 minus k by 3 into k minus 0 divided by 6 minus k by 3 will be getting only k. So this is a simple Routh array. So this highest degree is 3 only. From this, what is the range of k they are asking? So what is the condition for Routh array, Routh stability criterion? What is the condition? So we know the condition. The necessary condition for the Routh stability criterion is that the first column of the Routh array must be positive. If any one negative came, then system is unstable. So here they are asking range of k for stability. So system is stable. Then what is the range of k? So see, this is the first column. So this is the first column. So in the first column, it should be positive. Then only system is stable. So already we have 1, 3 is there. Both are positive. Then 6 minus k by 3 and one more term k is there. So this two must be a positive. So let it be k should be positive means k should be greater than 0. K must be greater than 0. Similarly, for this condition, 6 minus k by 3 must be greater than 0. Is it right? So both, if it is positive means both the condition must be positive. So k should be greater than 0. 6 minus k by 3 should be greater than 0. So 6 minus k greater than 0 means 6 minus k, if you take that side, greater than 0. Okay? 6 is greater than k. 6 is greater than k. So let's say k is less than 3. Then what is the range of k? K should be greater than 0 from this one condition. So k should be less than 6. So range of k we can write 0 to 6. That is 0 less than k less than 6. Okay. So within the range system is positive. For example, if we substitute 5, 6 minus 5 by 3, it should positive. 5 is positive. If the range of k is greater than 6, 7 is that means what will happen? This will become negative. Automatically the negative term will become. So from this we can find the range of k. So if they given open transfer function with the unity feedback system, then proceed with the characteristic equation, that is 1 plus g of s h of s equal to 0. Okay, then find the corresponding equation, solve the corresponding equation, then solve the characteristic equation by Routh array. If the system to be stable, check the first column should be positive. Okay, then find what is the range of k. Okay, is it clear? So range of k for this problem is 0 to 6. In some problem, if the practically if you see, the k should not be negative. Okay, if theoretically if we calculate and values k is become negative means, take the k value is from the 0 value. Okay, theoretically if you calculate negative value in some problem, this that means practically the gain should not be negative, so take the gain value from the 0 value. For example, the range is coming from, for example, minus 100 to 200 is that means take from 0 to 200 a range. Okay, the gain should not be negative value. Thank you.